Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 7.3, day 2, entitled Double Angle and Half Angle Formulas. And today we're going to talk more about the half angle formulas and how they get used. And I'm not going to show you how the half angle formulas get derived. I know I did that a lot with the double angle and the lowering powers formulas, but we're just going to cut right to the half angle formulas. And basically what this does is it helps you find a value that is an angle we know that's been divided by 2. Like if we had half of 30 would be 15. So this formula, if you were trying to find the sine of 15, it would be the sine of 30 over 2. And then you would plug 30 in here because you know cosine 30, and then you can simplify the expression after that. Okay? So let's take a look at our examples here. And we're going to oops, find the exact value. Now again, exact value means that we don't want decimals, because you could take sine of 22.5 in your calculator and get a decimal for it. But remember, decimals we round, so we chop them off and make them too small or too big. We want exact values. So that means we want radicals in there, and they're going to stay in that form, so that way we keep that exactness. So the trick to figuring these out to start with is to think, okay, 22.5 is really half of what? So you have to think 22.5 is half of something, and that something would have to be 45. Okay. Now here, the sine of 22.5, it's positive because we're in quadrant 1, so we're positive. Okay. So in these half angle formulas, notice there's a little plus minus in front of all of them. Okay, at least the sine and the cosine. So when we're dealing with the sine and the cosine, then we have to think, do I want the positive value or the negative value? So here we're in quadrant 1, where all the trig functions are positive, including the sine. So we want our positive value. So we're going to do the sine of 45 over 2, because 45 over 2 will get us the 22.5. Okay, so now I'm going to use that half angle for the positive sine value. So I want the positive square root of 1 minus cosine of 45 all over 2. Now the whole point of doing this is because I know what the cosine of 45 is. Okay, cosine of 45 is going to be square root 2 over 2. So now I'll have 1, minus the square root of 2 over 2, and that's all going to be over 2. So now we have to do some simplifying here, okay? I would probably start by breaking up those two fractions. So we'll have 1/2, and then we'll have square root 2 over 2 all over 2. So if I have something over 2 that's over 2 again, that's going to be over 4. So this is really the square root of 1/2 minus the square root of 2 over 4. And then I could find a common denominator. So 1/2 is really 2/4. So this is going to be 2 minus the square root of 2 over 4. And then, since I have a big radical and I have a fraction inside of it, remember to simplify those, you can break them apart. So I would have the square root of 2 minus the square root of 2 all over the square root of 4, and the square root of 4 is 2. So my numerator looks a little messy because I have the square root of 2 minus the square root of 2. But that's okay. You can have a radical inside a square root, a radical inside a radical. You can have that. But it's as simplified as I can get because I can take the square root of this denominator here. So that's my exact answer, because the decimal I get for that, if I just wrote it as a decimal, I'd round it, I'd chop it off. We don't want to do that. We want exactness. So it's kind of cumbersome the way it looks and the way we have to say it, but that's how it needs to be for us to get the exact value, to get as many decimal places as we possibly can. Okay, so now when we're evaluating expressions that have inverse trig functions, this is really something that you do a lot more in calculus, again, with our inverse functions. And here, we don't really have an inverse function so much yet, but we do have a skill that we know and apply with our inverse functions, which is drawing a little triangle. Okay, so they want us to evaluate sine 2 theta. They're telling us that cosine of theta is negative 2 over 5, and we're in quadrant 2. So this information here, where it says where blah blah blah, that's telling us that we've got to draw a picture for that and figure out the triangle and the other trig functions that go with that quadrant. So I'm going to take some time here. I'm going to draw my second quadrant. And remember, to get in the second quadrant, you have to go back and then you have to go up. So there's where my triangle would be, my right triangle. Okay, so theta is here. Now cosine of theta is negative 2 over 5. So adjacent over hypotenuse. Now this other side then will be x, and I can solve for that. So negative 2 squared plus x squared equals 5 squared. So that's 4 and 25. So x squared is going to be 21. So that side then is going to be the square root of 21. And it's going to be positive because we're going up. We had to go negative and then positive in order to get into the second quadrant. Okay, so now I have enough information to actually evaluate the sine of 2 theta. So sine 2 theta, that's my double angle formula. So look at your formula sheet or look at the previous section of notes. That's the same as 2 sine theta and cosine theta. And now that I know I've got sine theta and cosine theta, that's what I needed this triangle for. So I'm going to take 2 times the sine of theta will be opposite over hypotenuse, square root 21 over 5. And then cosine, either they told us or you could look at the triangle, negative 2 over 5. So then I'm going to multiply across the numerator. I'll have negative 4 square root 21, and across the denominator, 25. And I can't reduce that anymore. So again, this one isn't so bad because I get a nice exact numerical answer. Okay, last example then. This is like example number 7 in your book. So if you want to see another example of this one, take a look at example number 7. For the previous examples, let's see, example number 5, I believe. You could also look over example number 6 in your book as well. Okay. So look over example 6 and 7 if you need another worked out example before you tackle the homework. But this one for sure has the inverse trig functions in it because it has the sine to the negative 1 of x, so the inverse sine of x. Now remember, that means that the sine of something was x over 1. So that little piece of information there is very similar to what we had, whoops, what we had right here. Cosine of theta equals something. Okay? So again, I'm going to go off to the side here and I'm going to draw a little triangle. Got theta. Sine is going to be opposite over hypotenuse. And then I can do Pythagorean theorem to find this other side. Let me just call that other side y for now. So y squared plus x squared equals 1 squared. So then y squared would be 1 minus x squared. So y is going to be the square root of 1 minus x squared. So that's this side here. Okay, So now I have the cosine of 2 theta is basically how I'm going to rewrite this. Cosine of 2 theta, because I've done this inverse now to set up theta for any measurement. Okay, and I have to leave that 2 in front of it. So think of this as 2 parts to your term there. There's multiplication between the 2 and the inverse sign. And I know the formula for the cosine 2 theta. I have 3 of them to choose from. Doesn't matter which one you use. I'm just going to use the first one with the cosine squared x and the sine squared x. Oh, it would actually be thetas, wouldn't it? At x. Cosine squared theta and sine squared theta. Okay, so now if I look at my triangle, cosine is going to be adjacent over hypotenuse. So that's going to be the square root of 1 minus x squared all over 1. And I'm going to square that term because it's cosine squared. And then sine is going to be opposite over hypotenuse. So that's going to be x over 1 squared. So now they're both over 1, so that doesn't really affect me. I'm not going to have a fraction anymore. But in my numerator here, when I square this, 1 minus x squared, when I square that square root, I get 1 minus x squared. I get that radicand that pops out. And then here I'll have x squared. So I really get 1 minus 2x squared. Okay, so again, this is another type of problem here where these problems get really, really complicated and then it all simplifies down into something super nice. Okay, so dealing with this cosine of an inverse function, even when we have our inverses and we have our double angles in there, this is a really good problem because we're using a lot of our skills. We're using our basic trigonometry here with our right triangles. We're rewriting it in a double angle. We're breaking that apart and substituting and then simplifying. So this is a type of problem that you should be able to do on a test because you're using a lot of different skills here in one problem. So this is your homework to practice these concepts. It's a little choppy because we went through and picked out nice problems, appropriate problems that you'll need to practice, but they're all odd. So take a look at the answers in the back of the book after you've worked through them. And remember, the solutions are worked out in the binder in the classroom as well. And if you have any questions, come on in and see me before school.